Now let's look at a special case, so-called homogenization. Means making the material more homogeneous, making the material more uniform. You may deal with this problem like if you have a big piece from casting of material, or you have some others like polymer, same polymer but made over the time. You want to make them more uniform. Okay, so it's essentially using the phenomena of diffusion to eliminate local concentration, fluctuation, or variation to make the material more uniform. And what we have here is something like this. We have material, low concentration region, high concentration region, low concentration region, high concentration region. Of course, it may go back and forth. And the one thing that have a day-to-day example is like the Japanese ironsmiths, when they have big piece of metal, they hammer it into thin sheet and then fold it back and forth, back and forth, and then you have a high low, high low, high low, high low, and then they heat this thing together. The high should go towards the low, and over time this piece of metal become highly uniform in its carbon concentration, so that the material mechanical property become highly uniform. So that when you make a salt, one salt versus another salt, the property become uniform, predictable. Make sense? Okay, so it's very important. The simplest case for this so-called concentration fluctuation would be the concentration varies sinusoidally, follows a sine function, the concentration fluctuation. That's a very simple one. Okay, so we draw something like this: C versus X. C for concentration, X for location, okay, or distance. And we said, okay, the simplest case is for the concentration to vary follows a sine function, something like this. Okay, and then typically, if it's a sine function, we can write the analytical concentration equation as something like this: C, B for local solute within solution. Let's say B is our solute atom, and C bar. What does C bar mean? A sine function. Let's say C bar is the average of this sign. Okay, and then plus a oscillation term. What is the B0? That's kind of an amplitude of that oscillation, right? And of course, this is our sine function, pi x divided by L. L is, okay, from here, as you draw, as you see from here to here, it's actually half of our so-called period. Make sense? In this case, half of our period. The whole period is from here to here, right? So L is our half our period. When x equals 0, let's say it's 0. When x equals 1, sorry, not 1, but 1L, sine pi is also 0, right? So that's what we have. We have a sine function to describe the concentration variation. And then, again, this class is about model. Quite often the model we make simple assumptions to simplify it. Our assumption for simplicity is still diffusion coefficient is constant, doesn't change really with concentration. Okay, and in this case, our Fick's second law can be simplified to something like this: the d term goes out of the derivative term, partial derivative term. That's what you learned, right? Okay, and we said within from here to here is concave down, which means ends down, and mathematically means within from 0 to L, the second derivative of the concentration with respect to location is negative. And from what we learned, assuming D is also positive, this guy is negative, the concentration should, within here to here, should, of course, decrease with time. On the other hand, from L to 2L, it is concave up or ends up, which means mathematically the second derivative is positive, and from Fick's first law, second law, d positive, partial second order derivative positive, which means the concentration should over time increase, and so we have this, and the peak gets lower, the valley gets also shallower, and of course this is our new concentration profile, right? And the mathematical uh, goal would be okay to analytically describe. Once we have this second order partial differential equation, the end goal is to analytically describe how does local concentration change with location, and how does it change also with time. Okay, and of course we are not mathematics class, and what you learned in calculus or differential equation, we'll just simplify it here. The local concentration Cb for absolute B is a function of both location and time, and the solution, analytical solution, quite often takes this shape. C bar is still your average, and let's say the material doesn't lose material, the new material doesn't come in, the C bar should hold constant, right, over time. C bar, the average concentration doesn't really change because I'm not providing new material or extracting material. Plus this term. The B0 is still our original amplitude of this oscillation, and we have a sine term, sine pi x over L. But then we also have a exponential term that depends on time. The sine term doesn't depend on time, but the exponential term that depends on time. Okay? And then what it means is, okay, when x is 0, for finite time of t, when x equals 0, this pi x over L is, when x equals 0, this term is 0, sine term is 0, I'm just still here, right? When x equals L, I'm at here, L and the L cancel, sine pi is still constant, 0 for finite time. So kind of, okay, these concentration don't really change at here and here. And then if x are not at those special locations, when t increase, because we have that negative sign and we have the exponential, this exponential term should, when t increase, this exponential term should decrease, right? It's always positive because it's exponential. And when t goes to infinity, exponential minus infinity, that is 0, which means, okay, as time goes to infinity, this fluctuation become approaching 0. It doesn't really fluctuate. Please. Tau is what I'm going to say the so-called relaxation time. And it's a term that analytically is given this way. Good question. Tau is analytically given, of course we don't go into mathematical detail, L squared over pi squared d. What is L? That's our initial half wavelength. Make sense? And what is pi? Of course, that's a constant. D is also constant. So which means this tau term is a characteristic time, so-called relaxation time. So initially it's oscillating, and tau is this relaxation time. And when L increases, tau would, when L increase, tau would increase. Okay. When L increase, tau would increase. What that means is, okay, if the inhomogeneity is at a very large length scale, L is large. Remember, L is this, how long this high concentration range is versus low concentration range is. When L is very, very large, then remember diffusion takes time. Then of course, when L is very large, it's really going to take a very, very long time for this guy to be homogeneous, uniform. Make sense? On the other hand, what about D? When D is very high, what is the implication on the relaxation time? D is high means diffusion is fast or slower? Faster, right? D is high means diffusion is faster. For the same concentration gradient, more flux means diffusion is faster. And if diffusion is faster, if you can imagine the system become homogeneous in longer or shorter time? Shorter time, makes sense? So that's kind of an implication of the relaxation time, tau. And then the amplitude of the fluctuation is still going to vary for a given fixed time t. Remember, L is fixed, D is fixed. For a given system, tau is fixed. And if we look at a fixed time t, which means this whole exponential time would be constant, and then at any given time t, this still concentration follows that similar sign function, right? But the amplitude compared with the original amplitude, which is beta 0, would be slightly smaller. How smaller? It's modulated by this exponential term. The amplitude is modulated by this exponential term. Okay, and of course we see when t, the time goes to infinity, very, very long time later, this exponential term goes to 0, which means the relative amplitude becomes 0. Everything becomes uniform. Make sense? That's the amplitude of the fluctuation. This is the kind of first case for so-called homogenization. Quite often when you use for metals, especially steel and some other alloy. If you want your system to become more uniform, what can you do? If you want your system to become uniform faster, what can you do based on this? Well, you can either jack up the temperature so that you have faster diffusion coefficient, higher diffusion coefficient, shorter relaxation time, right? That's one thing you can do. Another thing is you start with try to make the non-uniformity region smaller. Makes sense? If it's huge non-uniform, then of course taking long time. Make sense? It's kind of like a linking the mathematical description to your day-to-day concept. Okay, so this is about homogenization.